The presentation is broken up into two sections. We'll take a break after the first, and then again at the end. The first half is on the manufacturing process and the products that we make, which are simple polymer pellets. And then the second half of the presentation is some application development work that we've done and how we can take advantage of the properties of PLA in specific application spaces. So why don't we get going? I'll show you the next slide. This is an overview of what we would refer to as a biorefinery. So this is a 600-acre plot of land down outside of Omaha, Nebraska, a little town called Blair, where corn is processed into its four components: sugar, protein, oil, and fiber. And inside the fence here, there are 6 or 8 other companies that all use one of those components as a feedstock in the products that they make. NatureWorks, of course, uses the sugar, and up in the top of the slide you can see the lactic acid plant. So the sugar is fermented to lactic acid and then passed directly next door to the lactide and polymer facility, which is circled there. So corn comes in by rail car at the bottom of the slide there, and numerous products leave this site, one of which is PLA. The next slide is a side view of the lactide and polymer plant. The fermentation at one point was part of NatureWorks, but over the years, that part of the process is now run by Cargill, specifically not by NatureWorks. So this is our building down on the site, and just for a little perspective, you can see a tall distillation column there in the middle of the screen. That guy is about 180 feet tall. The big tanks that you see at the front of the facility there, those are 5 million pound tanks for storage of lactide. And then the silos that you see on the right-hand side, those are finished products. So those would hold about 2 million pounds of product at a time. So that's what a PLA manufacturing site might look like. The next slide is the chemistry that goes on, and I'll break this out a little bit more individually as the talk progresses, but in a nutshell, the biorefinery provides starch and then glucose to the fermentation process. And I guess what I'd like to point out here is the atom efficiency of this. You know, we take glucose, which is 6 carbons, 12 hydrogens, and 6 oxygens, and really nominally turn that into 2 lactic acid units without losing any mass. So we've got 2 lactic acids at 3 carbons, 6 hydrogens, and 3 oxygens apiece. And that bit of it, is, as I said, is done now by a Cargill business unit. They supply us with the L-lactic acid. We make oligomers out of that and lactide, and then we polymerize that lactide to make our Ingeo biopolymer. And the other thing I'll point out here is, you know, from a bushel of corn, which is 56 pounds, there's about 33 pounds of sugar in that bushel of corn. And from those 33 pounds of sugar, we can get upwards of 19 plus pounds of PLA. And that includes the sugar that's used to grow the biomass and the biocatalyst organism for the fermentation process as well. So that's, you know, sort of all the way through the process. The next slide is you know, what engineers would refer to as a block flow diagram of the process. We'll start by looking at the oligomerization process, or what we would refer to as pre-polymer, and the lactide reactor there. So in that first vessel, we would receive an aqueous lactic acid product from the folks at Cargill, and that would self-condense. There's an alcohol group and an acid group on lactic acid, and that would self-condense to make oligomers. We would make oligomers of the desired length, and that gets fed then to what we would refer to as a lactide reactor, where lactic acid units 2 at a time cyclize and boil off of that otherwise condensed phase. The remnants from that are fed back to the pre-polymer section, where fresh lactic acid can get added to those, and we can rebuild molecular weight. With most processes, there is some sort of purge stream. So off of that process as well, things that come from fermentation that aren't lactic acid that would otherwise build up in the system are removed through a purge system. The next slide shows the chemistry that we would like to have happen in there. Some of the stuff that happens in there I can't tell you about, but as I said, nominally all we would like to have happen in there is lactic acid to condense to make these oligomers, and maybe we would target something around the 1,000 gram per mole target. With the heat required to do that oligomerization, there is some racemization of L-lactic acid to D-lactic acid, and that racemization allows us to make mesolactide, which is an important part of the feedstock that goes to the eventual polymerization process. And then the next portion of that is the lactide formation process. So I've got that drawn as, again, the backbiting reaction where a terminal alcohol adds to the penultimate ester carbonyl and makes the 3 isomers of lactide. So we've got SS or L-lactide, the RR or D-lactide, and then the SR or mesolactide molecule there. And those would boil off the end of this oligomer molecule. And then, of course, there's the remnants of the oligomer. If they're trimmed down to sort of lactic acid, or what we would refer to as DP4, they would be volatile and boil out along with the species of lactide as well. The next portion of the plant is the distillation process, and that is used to accomplish 2 things. It is used to remove, as I mentioned, the lower boiling or the lower molecular weight oligomers that come out of the lactide reactor, and it's also used to set the stereoisomer composition that's fed to the polymer reactor. So the specific ratios of bezo, D, and L determine the product quality or the product attributes of the PLA resin that we make. Distillation is a really efficient means to produce these lactide compositions. The other thing I'll mention at this point and on later slides is the polylactide that we make is produced via a ring opening polymerization. So the molecular weight is determined by the number of chain initiators that flow along with the lactide into the polymer process. So we need to control the number of remnant oligomers that are present in the lactide so that we can make the desired molecular weights. And this next slide is again, sort of the chemistry of the lactide distillation. Ideally, there would be no chemistry going on in that process because of the presence of the alcohol groups in some of the oligomers. It is a reactive distillation, but over the years we've learned how to tame that. What I've shown here is kind of the split of enantiomers, the SS and the RR or L and D lactide. Those are enantiomers, so those are not going to be separated by the lactide or by the distillation process. Mesolactide is a diastereomer of both of those enantiomers, and with that big column that I showed you on the third slide, we can separate efficiently mesolactide from the two chiral species, the L and the D. And the other purpose of the distillation process, as I mentioned, is to remove these light oligomers, what we would refer to as BP1, 2, 3, and 4, which are just dimers, trimers, tetramers of lactic acid that have some volatility as we distill the lactide. So at the end of the process, we've got a lactide stream that's got the correct distribution of lactide isomers and very little to none of these alcohol-containing species that they were made from. The next slide is meant to show the consequences of stereochemistry. So lactic acid is has a chiral center, and it exists as two enantiomers. The biological or fermentation process is very good at delivering a single L isomer. If you were to trick out an organism, you could have an organism that makes mainly or only D-lactic acid as well, but that would be a whole separate process. As I mentioned, the oligomerization process has some thermal history to the lactic acid, and that allows us the opportunity to interconvert some of the L-lactic acid to D-lactic acid, and that allows us then the opportunity to make mesolactide and some D-lactide. Now, the composition of that lactide stream can be approximated by the binomial that I've shown here, the weight percent or mole percent of L-lactic acid and the mole percent of D-lactic acid squared gives you the nearly the relative ratios of lactides that we're going to make. So as an example here, a lactic acid stream that's 90% L-lactic acid that's fed through our process of oligomerization and then on to making lactide would produce a stream that's about 81% L-lactide, 18% mesolactide, and 1% D-lactide. Now, as I mentioned earlier, the L and the D-lactide are enantiomers, so those we cannot separate. But if from this stream, if we were to remove all of the mesolactide, we would end up with a stream that would contain 1.3 weight percent D-lactide and 98.7% L-lactide. So, via this distillation process, we can produce a lactide stream, or we could produce a lactide stream from this example with anywhere between, let's say 0 and 18% mesolactide. Moving on then to the polymer process, we've got our set mixture now of LD and mesolactide that we're going to feed to the polymer process. This is a melt process, and it is a reversible equilibrium-based process as well. So, as I mentioned earlier, we control the molecular weight by the number of chain initiators that we add at the beginning of the polymerization process. Depending on the temperature of the polymer reactors, that sets the ultimate extent of conversion. So if you think about a process being run at, let's say, 180 degrees, you could consume up to or have an equilibrium lactide concentration at the end of the polymerization of about 3.5%. If you increase the temperature, the amount of equilibrium lactide present at the end goes up a little bit, so it would maybe go to 5%. The other thing I'll mention is that this is all done in the melt. The reaction mass needs to remain above the melting point of the polymer that we're making so that it doesn't crystallize out on the inside of the reactor as it's being made. This melt stabilizer arrow that we've got here is a catalyst deactivator, and that is added to prevent reformation of lactide during the monomer recovery step and also during subsequent processing by converters. We don't want the polymer chains, when they're heated up in an extruder, to head back towards you know, the 3% equilibrium lactide that's present. The next slide is again just kind of the chemistry update there. We start with a lactide molecule. In this example, you know, I'm showing lactic acid being used as a chain initiator and going to a mixture of residual lactide or equilibrium lactide and polymer. After deactivation of a catalyst, we would then vacuum out the residual lactide or the equilibrium lactide and deliver just the polymer melt. The devolatilization takes place in a vacuum chamber, and the recovered lactide can be recycled back into the process, so that's not a waste stream. This last kind of upper right-hand section of the block flow diagram is a relatively new capability to NatureWorks in the last few years. The distillation process, as I mentioned, it's a very efficient way to deliver mixtures of meso D and L, whereas a crystallization process is really focused and is most useful for delivering, you know, very pure single isomer type feedstocks of lactide. So we've added a couple of new products over the last few years derived from very pure L-lactide, so a polymer that's built from 100% L-lactide. In this instance, I guess I'll mention that in the crystallization process, we are able to enrich the enrich the stereoisomer content or the enantiomeric excess of the L-lactide, so it is possible to remove D-lactide from an L-lactide stream via crystallization, because the L-lactide basically acts as the chiral resolution agent in the crystal nucleation process to give us something that's enriched, a crystal that's enriched in L-lactide and a supernatant that's enriched in D-lactide. So that's a phenomenon that works in a general sense when you have a stereoisomer population that's you know, better than 90% to start with in the first place. We can also use that crystallizer to purify and isolate mesolactide as a purified polymer grade material as well. And what I've shown here is, you know, we can feed from either of those tanks back into the polymer process, so we can use those materials to supplement what's coming off the distillation process, as well as using them as single feeds. The next slide is kind of a cartoon of a polymerization process where you've got a mixed stream of L-lactides, which are the two green dots, D-lactide, which is the two red dots, and mesolactide, which is, you know, one green, one red. In the first instance, we've got a D-lactide now isolated between a couple of L-lactides. Generally speaking, you know, L-lactide is always going to be a minor component, and so it will typically be isolated by itself. It will generally not be adjacent to another D-lactide or adjacent even to a mesolactide necessarily. And and then the mesolactide can get incorporated into the chain. And depending on the polymer that we're making, we will have, more or less of that material present, and sometimes those molecules have a probability of ending up adjacent to one another, and they can go in either orientation, either in this top screen, which is what I would say is head-to-head, or in the bottom configuration, which would be head-to-tail. The next slide kind of gives you an indication of the various polymers that we make at NatureWorks, all the way from the top material, which is for all intents and purposes a true homopolymer of L-lactide. That would have a melting point in excess of generally of 175 degrees. It would be a very rapidly crystallizing PLA material and crystallized to a great extent. And then as we start to introduce comonomers, either D-lactide, mesolactide, or mixtures of those two, we can suppress the melting point of the material, suppress the crystallization rate, and suppress the extent of crystallization of that material. And if we make something that has a substantial amount of mesolactide or all mesolactide, we can make something that's truly amorphous, that using the catalyst and process that we have in Blair will make a truly amorphous material. The other thing I'll mention is that you can see the glass transition temperature is depressed slightly as we add bits of D-lactide and mesolactide, and the all mesolactide polymer is significantly depressed from the kind of the 60-degree glass transition temperature that people think of for PLA. The bottom configuration there is what people would refer to as stereocomplex, and that can be made from either a blend of what I will call PDLA, so poly-D-lactic acid or poly-D-lactide, and PLLA or poly-L-lactide, or it could be even a block copolymer made from those materials, as long as the block length is in excess of about 40 units. That material will crystallize to give a much higher melting material of about 220 degrees. And this phenomenon is really often seen with racemic mixtures, which is what that polymer is. In fact, the melting point of racemic lactide is about 125 degrees, which is up from the 96 degrees melting point of either L or D lactide. And most racemic mixtures do have a melting point that's higher than either purified enantiomer. So this is not necessarily something that's unique to lactide or PLA, but something that is sometimes useful. Now this last slide here, or the next slide, is one that shows the decoupled NMR spectra of the methine region, so the CH space of a polylactide. And what I want to show here is that, I've spent a fair amount of time, I guess, pointing out that, we're a copolymer of D-lactide, mesolactide, and L-lactide, and sometimes the D-lactic acid content can be instructive or a useful analytical assessment of the polymer to help describe the properties that it will have. But here's an example of three polymers that, if you were to analyze them, would all come up 50% D, 50% L. And how would you tell them apart? Well, proton NMR is one way to do that. And so in the upper left, I've got an NMR spectrum for polymeso. And if you think about that, the minimum block length there is 1. If it's a rigorously alternating addition, head to head, and the maximum block length would be 2. The spectra on the upper right is a poly DL or poly rack. That would have a minimum block length of 2 if it were rigorously alternating, and could have a maximum block length of just about any number you pick. And as I mentioned, if that block length gets up above 40 or so, a polymer made from rack lactide will look an awful lot like a stereocomplex material. And then the NMR spectra on the bottom left is a spectrum of poly L and poly D lactide. So that would be a spectrum of consistent with stereocomplex PLA. So we'll end here. This is, again, this is the product that we make. Here's some pellets coming into a bag. We have a number of series of products that come out of the factory down in Blair, as well as lactide monomer itself, and it goes into a number of applications. But we can stop here if there are some questions. Okay, so the second half of the presentation is on commercial applications and some of the development work that we do internal to NatureWorks to help bring some of these products to market. As you saw in the first slide, what NatureWorks sells are the pellets, and other converters, I'll call them, turn the pellets into things that consumers would see or buy or other folks would use. And I've got 3 examples of processes that we've helped develop, or products where PLA has some attributes that make it a good fit for use in those particular applications. And I've tried to in some of the applications, show a bit of the science that goes into that product development process that's done at NatureWorks, to give you kind of an idea of what happens in the commercial world and at a business like NatureWorks. So the first one is a bit on rethinking coated paper serviceware. So this is, paper cups, which might not sound all that interesting, but if we rethink where your serviceware comes from and rethink where the serviceware goes after use, a typical paper cup is made out of paper and it's coated with polyethylene, and the polyethylene is there to keep the moisture from soaking into the paper and ruining the cup. Well, from a recycle point of view, that cup now is a mixed stream. It's got paper and it's got polymer, and those would need to be separated from a recycle point of view. And from a composting point of view, while the paper component is compostable, the polyolefin isn't. And so the question is, can PLA deliver to consumers and venues, like stadiums or universities, a cup that's wholly compostable? That would be a benefit to all. And we can do this for both hot and cold cups. But there are some performance requirements that need to be met. And the first and foremost is for a drinking cup, it needs to be food safe. And then on top of that, for some of these, we would like a compostable certificate, and if we could get 100% bio-based content, that would be good. From the cost-effective point of view, there's a couple of points here. The material needs to be able to run at competitive speeds to somebody making a paper cup out of with polyolefin. And the extrusion process has to be stable and work well. And there are some trade-offs between the cost of the goods, what you pay for the cup and what you pay for the disposal. So in a typical venue, there would be some waste hauling fees, and if your material is 100% compostable, you can often trade your garbage hauling fees for some composting, where the composter isn't going to charge you quite as much to pick stuff up, or may not charge you at all. So this would be an example where the compostable nature of PLA would provide a benefit over a polyolefin. Now, there are, as I mentioned, some performance requirements that have to be met in order to convince people to make the change, and those performance requirements are around melt strength and curtain stability of the melt, and some adhesive properties. So melt strength is important with respect to neck-in. So if you have poor melt strength, as you see here in the cartoon, what comes out of the die will get significantly narrower as it gets stretched and applied to the paper substrate. Melt curtain stability refers to what we would call edge weave. As you pull on that material coming out of the die faster and faster, you'll set up a resonance where the edge of the material will wander back and forth. If that's extreme, you'll end up with some yield loss, because the paper that gets used can only be as wide as the narrowest of the coated material. And then the third thing I've mentioned here is adhesion. So it has to, the polymer has to adhere to the paper with sufficient strength, because it's actually the glue that ends up holding the cup together, as well as providing the protection for the paper from the liquid that's inside. The other part of it is, I mentioned the heat seal. It's the glue. Part of it is toughness as well. So we've got a sidewall and a bottom, and this bottom is going to get punched and a pleated skirt put in it, and the polymer needs to stay attached to the paper stock all during that process. If it flakes off, we're going to get poor formation of the cup and poor integrity of the cup. The next slide is, I guess, is my attempt to show you how sophisticated we are here. We're not going to go through the math, even if we had time. But the extrusion process is an extremely complicated process. There's a lot of things changing as a function of time. And in order for us to develop products related to this extrusion process, we need to have an in-depth understanding of the process and what's going on. And so there's a number of equations here. This dF dx has to do with the force applied as we're pulling the extrudate out of the die. That dL dx term has to do with the narrowing of the melt curtain as it comes out of the die. The dV dx has to do with the distance and the velocity of the polymer melt. The paper stock is typically moving much faster than the melt curtain, and so the material coming out of the die is being drawn down as it's applied and adhered to the paper. And then there's a whole bunch of temperature dependencies as the material comes out from the die lip at its extrusion temperature, and then through the air and going over the rolls. There's some heat loss and things like that going on as well. And temperature plays a critical role in all of this, because viscosity of PLA is very sensitive to temperature, and the viscosity of the material is important in this neck-in process and in the adhesion and adhesive process. So this next slide shows some of the modeling work that we did, where we were keeping track of all of those temperatures and parameters. On the left panel at the bottom of the slide, you can see a melt extrusion, and the cardboard is there to help you see the extrudate come out. And you can see the neck-in of the process there. And on the right, you can see some infrared images to help us keep track of the temperature. And so we could put all of those inputs into a model. And you can see on this next slide, we have some model validation. And so if you look at across the top of this is the melt temperature. And then as you go down through the slide, you can see distance from the die. And if you start in the upper right-hand corner, you can see the melt temperature drops off as you get further and further away from the die. And that melt temperature then impacts the viscosity and the properties of the polymer as it's cooling and as it's hitting that chill roll and being applied to the substrate and trying to be set. So this is a first step for us to model the process and then get a handle on some of those secondary processes. The next slide shows a balance of viscosity and melt strength, and two things that we're trying to accomplish at the same time. The viscosity, or typically these would be at odds. The model and the experiments eventually lead to products that balance these two needs. You can see the green shaded area that represents the current commercial grades of polylactide. The orange line represents branch PLA, which would be done, or could be done with some peroxide chemistry that we talked about earlier. The yellow line shows the incumbent LDPE, or low density polyethylene. And you can see that it hugs the bottom of these curves. It's a great polymer for that, but it's not compostable. And if you notice the Ingeo 1102, that is a formulation that we were able to develop that is a good compromise of melt strength and adhesion, and with the added benefit of being compostable. This next slide shows the effect on coat weight, and coat weight would be the name of the game, as it's directly related to the cost of the material used. The more of it that you put down on the paper stock, the more expensive the cup is going to be. We need to have sufficient coat weight on there to get adhesion. As I said, that's the glue used to hold the cup together, the sides and the bottom. And you can see with the new formulation, even at these low coat weights down to about 15 grams per square meter, we still get great adhesion of the polymer to the paper stock. And with regard to neck-in, you can see we've made about a 30% improvement in neck-in compared to neat PLA. The next slide shows what this process would look like. You can see the black colored pieces on the left-hand side there. Those would be cut out or cutouts or punched out of a sheet of paper stock, and then it gets rolled into a cup. You can see the pleated skirt at the bottom and in the middle of the top picture, and the rim roll at the top of the right-hand side. So again, it's important that the polymer act as a glue, stay attached to the paper stock throughout the whole process. And we've got some what we would refer to early adopters. These are converters that are looking for new products and who want to stay ahead of the curve. So these are some materials that we hope to be commercial successes later this year. The next example has to do with personal hygiene or diapers. And I guess I'll say that diapers are really very sophisticated articles. There are many components to them. And anybody that has kids knows that if there's a failure, it can be unpleasant. You'd like them to work the way they're designed. a typical construction would be a polypropylene in this case, but PLA offers several advantages due to its much more polar nature or hydrophilicity. I've shown here on the left-hand slide or side of this slide the four kind of components of a diaper. We've got a top sheet, which is against the skin. The liquid moves through this top sheet to what was labeled the ADL, or the acquisition and distribution layer, that spreads the insult, the water, urine, across the superabsorbent, which is typically a polyacrylate, and then the back sheet is basically the outside of the diaper. And you can see here on the right-hand side, the property that's really a key feature here is the surface energy of PLA, almost 71 dynes per centimeter versus the very non-polar polypropylene down at 47 or 48. And that difference is important, or the high number for PLA is important for a couple of reasons. Typically, the fibers, every fiber is going to have some sort of finish or treatment on it for processing and for use. And the high surface energy of the PLA helps that surface finish stick as well as be more efficient. This next slide shows some of the performance attributes of a PLA top sheet versus a typical polypropylene or polyethylene or polypropylene top sheet. And as I mentioned on the last slide, the hydrophilicity or the surface energy of the PLA allows us to use half the finish on yarn that a typical polypropylene fiber would use. And these are all non-woven spun-bond type materials. The other attributes that are here are strike-through, runoff, and re-wet. And in these cases, strike-through is the amount of time that this is a standardized test, the amount of time that it takes a volume of water to pass through the top sheet. And you can see even with half the finish loading, we're at or better than a typical or a standard polypropylene. Runoff is a measure of, again, of wicking ability. In that test, it's the amount of water that makes it across an angled piece of fabric without soaking in. So we pass that test with no material reaching the edge of the fabric. And then this re-wet is the measure of the ability of the water to pass back through that top sheet if the SAP layer is compressed. And so what you would like to see there is, again, is a very low number, and in fact we do better than polypropylene in all three of these cases. So all of this leads to sort of better skin care and less skin irritation. The next slide is meant to show the attributes of PLA with respect to water vapor transmission. We have a rather, or polylactide has a rather high water vapor transmission rate, and that can impact skin health as well. So this is an example of Candida albicans is a human skin pathogen that grows best in a warm, moist atmosphere. So in totally occluded skin, so that's wrapped up, which would be something like skin underneath a polypropylene diaper, you have good survival of colonies and good growth of that yeast. The more breathable the material is, the drier the skin can remain, and the less yeast growth that you'll see. And this is a benefit for skin health. the next little example that I'd like to go through is a case for, again, back to food and dairy and dessert packaging. And so you'll notice that in retail markets today, there's a drive for clear packaging. Consumers want to see what's in the carton or the package that they're buying, and how can PLA be an advantage there? Typically the polymers that are used for this sort of packaging are amorphous polymers, and that's because they're clear crystalline polymers tend to be hazy or pick up opacity due to the scattering of light of the large crystals as the polymers crystallize. A typical choice or material that's used in this sort of packaging as an incumbent would be polystyrene. So a regular high-impact polystyrene, because of the impact modifier that's in there, that material becomes very hazy, even though it's still amorphous. The polystyrene industry solved that issue by coming up with some styrene butadiene copolymers that are added as impact modifiers to bring the haze down. And NatureWorks or Ingeo has impact modifiers as well that will allow us to deliver very haze-free or very clear material as well. Well, what are the other attributes of PLA that would make somebody switch from these high impact or these clarified polystyrene formulations to a PLA? And one attribute that we have is our stiffness. And so if you look at the graph on the left here, the stiffness or the modulus of PLA is about 40% more than a typical high-impact polystyrene that would be used to make these, in this example, yogurt cups. And then the question is, well, how does that 40% increase in stiffness, what does that buy you from the consumer point of view or from the packaging point of view? And the answer is it allows you to do some down gauging to reduce cost and the weight of stuff that's being shipped around. And a very tangible benefit or utilization of that extra modulus is in what we would call a top load strength. And so you can see here for and that's the sort of the stacking load on a number of, again, in this particular example, it would be yogurt cups. If you look at the top load strength, if we say it's a little over 0.003 newtons, you can reduce the sidewall thickness from about 150 microns for polystyrene down to about 100 microns for Ingeo. And where that comes into play then is the top load strength impacts how many cartons you can stack on top of each other inside a box and not worry about the cartons on the bottom or the yogurt cups on the bottom getting squished or broken by the weight of the ones on top. So this difference in down gauging can also help compensate for differences in density between the two polymers and the pricing per pound of the polymers. And there's yet another benefit to PLA that's again inherent to the material, and that has to do with the natural O2 barrier and flavor and aroma capture within the packaging. So shown here is the top one is the oxygen barrier. You can see is much lower for Ingeo or for PLA compared to polystyrene. That leads to longer shelf lives. The lower aroma thresholds keeps the flavor in the food and the smell out of the refrigerator. And then, this is something that we would have led with in our early days, but, now only after delivering on price and performance can or do we mention that, Ingeo comes with a lower carbon footprint. So in comparison to polystyrene, we use less energy to actually make the polymer itself, and we consume, a significant amount of greenhouse gas in the production of the monomer, and therefore the polymer. And I've just got 2 more slides here, and what I wanted to present to you guys here was kind of a revamp, and this may be the first public exposure of our new mission and vision statements. We've grown and undergone quite a bit of change in the 16 years that I've been at NatureWorks since early 2000, and we wanted to come up with something that captured what drives us today. And I guess given the audience, I wanted to show you that we are driven by curiosity, and we say we're obsessed with science, and I would attest to that. I work with a group of really first-rate and top-notch scientists and individuals here, and we work every day to make our manufacturing process better, and the products that people make from our material more versatile and better solutions to consumer problems. And then the last slide here is a restated of our ambition, and it says from scrappy pioneer to market leader and beyond. And we were the first, or NatureWorks was the first to have a PLA plant with appropriate economy of scale so that we could compete on a cost basis with the other major commodity polymers, things like PET and polypropylene and polystyrene. Our plant in Blair was built with very large equipment and very much built with a mindset of build it and they will come philosophy. And after a number of years, the plant is nearly sold out, or becoming sold out. And we're world leaders today, but you guys may be aware that a company called Corbion or Corbion Total will be supplying material to the marketplace soon, which is a good thing, so that as our plant becomes sold out, that people still have access to material. And I guess the last thing, or one of the last things I want to say is, as the first large-scale producers of PLA, we couldn't simply drop off a bag of resin, at a cup manufacturer or at a fiber spinner and say, have at it. We really needed to go in and teach those folks how to use the resin and help them develop products. So here is the last slide, and what I tried to show you with those couple of examples from the application side of things was, how we take advantage of the inherent properties of PLA, and in the paper coating examples, we needed to engineer in some new melt strength, to help us enable the advantage of compostability. In the hygiene example, we take advantage of the natural hydrophilicity of the PLA to provide, improved performance. In the dairy and dessert, we take advantage of the natural stiffness, the clarity, the oxygen barrier, and we can tout the carbon footprint benefit as well. So with that, I'll stop and I guess open it up to questions.